Hello again and welcome. Today we're going to be revisiting the NISSEI RS-70 watt meter. And this watt meter was good for 1.6 to 60 megahertz. During the initial video I did a review of this and we found that it wasn't very accurate. And then I did a part 2 where we reverse engineered the coupler. And this was the schematic for it. So during that video I pointed out that they have a piece of coax that runs between the TX and the antenna, and that coax braid was never terminated to ground. So I had taken an X-Acto knife blade and I laid it across the very tip of this down to the ground, and we looked at that with a network analyzer, and that improved the frequency response quite a bit. So I asked people that had one of these that worked meaning that they had actually measured it and they were getting accurate results, to take theirs apart and have a look and see if that braid was terminated on theirs. Unfortunately, not one person came forward and provided any details about that. So what we're going to do today is we're going to attach a braid to this piece of coax and see if we can get this thing to improve a little bit. So it looks like we have a little bit of hot glue maybe in here. Yeah, that's definitely what this is. I think to do this right, what I'd like to do is go ahead and pull this coax right out of here. We'll trim it back and then we'll re-terminate it. So let me get the soldering iron out and the heat gun. Go ahead and remove the bottom screw just to gain better access to this. Here you can see I've just unsoldered the 4 wires going to the transformer. Here's our coax. We've gone ahead and removed that. Now let's just lift this piece right out of here. Shouldn't take much to get that glue to give. Next we'll take our X-Acto knife and we'll trim back a little bit of this insulation. You can see the glue didn't really adhere to the insulation. So I just slid this thing out a little bit to gain better access to it. So what we'll do now is take another piece of braid and I'm going to solder to that. So we'll go ahead and change out our tip. We'll use a wedge. Cut off a little piece of coax and then I pulled the braid out, and I've used a set of flat needle nose pliers to flatten this thing down. We'll go ahead and tin this like so. That'll just prevent the end from fraying while we're connecting it to our other braid. So trim off the end here, get a nice clean cut. Next we'll be using our round-headed needle nose, and we'll wrap this into a little circle. So because these two pads and this entire plane are at ground, what we'll be doing is attaching our braid in this direction, so it'll essentially be sitting flat against that ground plane. So it'll come off like this. Alright, then we can just go ahead and solder these two pieces together. Like so. Next we'll go ahead and cut that off a little bit. You can see we want about maybe a 1/4 of an inch or so. We'll just snip it right about here. You can see once we solder the coax back in place, it's going to make a real good contact. Next we'll go ahead and reattach our transformer. Next we'll just take the heat gun and we'll reflow that glue. You can see that stuff melts very quickly. And we'll just let that harden back up. Looking at the UHF connector, you can see that they're using almost like an air line here. I assume that they've done that to get the higher performance at 60 megahertz. Again, we'll just be using some UHF to N adapters. These were just some cheap ones that I bought off of Amazon. So looking at the schematic, I've gone ahead and updated this. So you can see I now show the ground for the two connectors. That's pretty obvious. You can see I've also gone ahead and added our braid. So the next thing what we want to do is place this thing onto the network analyzer and we can go ahead and try to compensate this and see how flat we can get the frequency response. So again, we'll be using the HP 3589A. One of the very nice features again with this is that it does support a 1 mega ohm input, so we can use standard oscilloscope probes with this if we want to. So again, the way we'll connect this up, we'll attach our source to the transmit side. Doesn't really matter, but that's the normal way that would be running. So let's see, we want to go to measurement type, and we'll do swept network, and we can set our frequency. We'll do start frequency of, I don't know, a megahertz, and we'll do a stop frequency of 60 meg, and we can go ahead and select our input range, and we can set this to a 1 mega ohm input. Let's see how our calibration looks. And we'll just do transmission normalize, and you can see it's basically reading flat at 0 dB all the way across. And now let's have a look at the output of the transformer. Wow, that is so flat compared to what it was. That's impressive. Let's do scale, and we'll just do an auto scale for the vertical. I mean, that's a half a dB per division, so 1, 2, 3 dB down right there. Let's just look at the other side of the transformer. It should be the same. And you can see it roughly is, if I could hold my fingers on there. Again, it's a little tough. What I'm trying to do is get our little ground probe into one of these vias that are nearby, and then attach the probe. So there you can see it. So let's see if we can flatten this thing out a little bit. Again, we have this compensation capacitor here. Can't use a metallic screwdriver, so we'll just be using this diddle stick. So again, it's a half a dB per division, so it's about 2 dB down right there. That's about as flat as I can get this using their little trimmer capacitor. So that adjustment is done. The next thing what we need to do is calibrate the two pots. So to do that, we'll have to use a watt meter. So before we try to align this, one of the things I thought I'd mention is a lot of times I'm on the forums and I'll see people post photos of whatever they're working on, and they'll have all their connectors just laying loose in a box, just bouncing around in there. And you can imagine what that's doing to all these precision connection points. You know, you're just destroying them. This one happens to be an ammunition box. You can get these things fairly cheap for a couple of bucks maybe. Just go down to your local gun shop. This is another one that I put together a long time ago. You can see I just laid a piece of plywood in here and I drilled it out for the various connectors. So I have my RF generator attached to a wideband power amplifier. That amplifier is good for easily up to 60 megahertz and down to a megahertz or so. So we'll use that to provide our signal. Then the antenna side is just going off to a power attenuator. It's going off to a thermal sense head. I've got a Rode Schwartz watt meter here, and we'll be using that as the reference. So looking at our data sheet where it says calibrated center, so that's between 1.6 and 60 megahertz. So the center frequency is probably, we'll call it like 30 megahertz. So what I'll do is I'll calibrate this for 27 megahertz. So basically in the area of the citizens band. Now I've gone ahead and marked our two pots. So our pot on the left, this is to set the forward power. Now again, I have a 30 dB attenuator attached on the output of this. So I'm going to be setting the power amplifier for 20 watts. That's a 43.01 dB. We subtract off the 30, so we'll have 13.01 dB. So this should be 20 watts right here. I can get our diddle stick back on the pot. Let's just adjust this thing up and see if we can get 20 watts out of it. Right about there, I'd say. It's pretty close. So now what we're going to do is turn off the power amplifier just for a sec. Should go back to reading 0. There it goes. And now what we'll do is flip their two connectors around. So we're transmitting into the antenna side. Again, this is a bi-directional watt meter. Again, with that 2 dB of flatness, I'm not expecting this is going to work very well. Alright, let's go ahead and we'll turn the power back on. And we can see it's reading what? 12.15. So this should be reading 20 watts both directions. Let's see here. Huh. Oh. Put the screwdriver on the wrong side. We'll have to reset the forward power again. Alright, so crappy USB connector fell out. There we go. One more time. So, oh, wrong direction. There's 13, 14, 15, 19, 2007. Right there, 20 watts. Alright, one more time. We'll turn the power back off. And we'll flip our two connectors around. Put the diddle stick on the right pot this time, hopefully. Alright, and we'll turn her back on. Of course, we got 14 watts now. Imagine that. Forward power pot. Again, we'll this time get around the forward power pot. Oop, wrong direction. And again, we'll set this back to 20 watts. Very good. Alright, so the next thing we'd like to do is look at the SWR. So again, I have all these loads here that I made up. So for example, this is a 150 ohm resistor. This will give us an SWR 3:1 or a return loss of 6.02 dB. I've got a few different ones. This one's 200 ohms. There's a 25 ohm. Here's a 100 ohm. Here's a 10 ohm. And this one is a 75 ohm. Let's just start there at 75 ohms. The problem with these is they're not rated to handle a whole lot of power. And of course the watt meter can't read very low power. So unfortunately, we'll probably have to cook these things to get this to work. Let's just see what happens. So I'm expecting this to give us a VSWR of, again, 1.5 to 1. Let's just see what happens. So we'll turn up the power. Yeah, even at 20 watts, it doesn't seem to pick it up. It always reads 1 to 1. This is a, well, let's just try it with an open. I mean, that should read a very high VSWR, right? Yeah, 99 to 1. Yeah, basically 100 to 1. Alright, so I don't think this is going to work no matter what we do with it. So right now I'm putting out about 10 watts. Now I'm putting the power into the antenna side. And you can see this is reasonably close. It's about 10 watts, and again the output is terminated to 50 ohms, and you can see it's reading an SWR of 100 to 1. The reflected power right now is 0.05 watts. Again, it's a very good load, so we're expecting it's basically not going to have any return power. But let's go ahead and we'll flip these two connectors around. I'll just leave the amplifier running. And let's go ahead, we'll reattach our load. And you can see we're reading roughly 10 watts. Forward power, 0 reflected. So right now, again, the SWR is reading 1 to 1. Let's just attach our 100 ohm resistor again. This would give us an SWR of 2 to 1. So with nothing attached, you can see it's reading about 14 watts forward and 26 reflected. Alright, so let's go ahead and we'll attach this now to the output. Let's see what happens. Okay, so it's saying a reflected power of 0.00. The forward power is reading 10.5. I know that's not accurate. This thing should be giving us a 2 to 1, and this thing is definitely putting out a fair amount of power. She's getting hot real quick, and these resistors are not rated for 10 watts. So let's go ahead and we'll pull this back off real quick. Again, that was 100 ohm. Let's try it with a 25. So you can see our forward power is reading 9.17 with a reflected power of 1.53, and we're getting an SWR of 2.4 to 1. Again, she's starting to get pretty hot. That's interesting. So as we go up in resistance, it's not very accurate. What did I say? I had another one here. So this is a 10 ohm resistor. Should give us a 5 to 1 SWR. And notice this. Again, it's reading a higher reflected power than the forward power. So I don't think, unfortunately, that we can really do anything to improve this. This is just a bad design. So I was hoping that when I connected that ground strap that we'd actually get an even flatter response out of this. Unfortunately, didn't work out that way. But my original plan was to benchmark that against another watt meter. This one happened to be made by Paradynamics. It's a model PDC 600. This watt meter is really old. It was sold to the CB operators. You can see it has a 10, 100, and a 1 kilowatt range. It also measures SWR and %AM modulation. So I've aligned this meter for 27 megahertz. That's where the factory aligns it at. So if we look here at 5 watts, at 27 megahertz it reads 5 watts dead on. At 20 watts it reads 20 watts dead on. But notice at 50 megahertz it reads 6.5 watts and 25 watts. At 14 megahertz it's reading 3.5 and 15 watts. 7 megahertz, 1 watt and 4 watts. At 3 megahertz it's all the way down to 0.3 watts and 1.8 watts. Now this watt meter was originally supplied with 4148 diodes. I've replaced that with a low drop Schottky. It did help the sensitivity somewhat. If we look at the modulation on this, comparing it against my RF generator, this is actually quite accurate, up to about 80% or so. And the SWR is pretty much dead on. Even when you're looking at these low frequencies, it's pretty much spot on. You just have to apply enough power for this thing to be able to detect the forward and reflected power. But you know, if you're putting out, I think I was running at maybe 20-30 watts, it actually worked quite well at the lower frequencies. It's really just the RF power level that isn't accurate. Well, I think that's going to be it for this video. Hopefully we've all learned something from it. If you're really looking for a good watt meter, I don't really know what I would recommend. Again, I'm not a ham operator or a CB operator, so I really have no need for such a device. I do have that precision watt meter from Rody Schwartz, but again, that's not an inline system. The one that I built, again, it works pretty good. The difference being I spent a lot of time and effort to try to get the directional coupler working. Again, the coupler is really the heart to this. You got to have a very good directivity and a very good flatness. even if you're trying to compensate for those with software, there's only so much you're going to be able to do. Well, I think that's all for now. Hopefully you enjoyed the video. I do have some plans for some up and coming videos. I posted up on the forums to see if anybody was interested in running another low-cost meter shootout, and I got a couple of meter recommendations, and some of those have come in. Of course, there's this one here from Unity. We all know that the grill starter is probably going to kill this meter. I'm not expecting these are going to survive our transient generator off on the right here, but that's my plan, is to start reviewing these. You can see I've got one here from Klein. Here's an Astro AI. Here's one from Kiwit. There's a few more left that haven't come in, but if you're interested in seeing some cheap meters tested again, stay tuned and we'll start looking at those over winter. Till the next video, later.